Our topic today is a very important one. It's aptly named 7.4, the fundamental theorem of calculus. And the name should suggest that this is a super important theorem, and indeed it is. It underlies, hence the name fundamental, it underlies pretty much all of calculus. But before I tell you exactly what's happening there, let's just recall really quickly how differentiation worked. Right, so you've got a function, y equals f of x, and I want to find the tangent lines of this function at x equals a. So I haven't drawn the best tangent line on here, but the red line looks like it's roughly tangent to the curve at x equals a. And what we want is we want the slope. The slope of the tangent line is what we call the instantaneous rate of change of the curve at a. So the slope is the derivative, f prime of a. And we originally defined this by looking at secant lines and pushing points together and coming up with this limit definition. So our limit definition was that the derivative at a, f prime of a, is the limit as h goes to 0 of f of a plus h minus f of a over h. And we computed a few derivatives using this limit definition, but all in all, it's pretty hard to use. Well, what do we do then? Then came in these rules, this power rule, the derivative of x to the n is n times x to the n minus 1. Power rule, quotient rule, chain rule, I forgot one, the product rule. And using all these rules together, now differentiation became a whole lot easier. A whole lot easier than having to use this limit definition. Right, so we had sort of these rules that came to the rescue, and we didn't have to use this complicated limit definition anymore. And with some movie magic, this appears next to me. But yeah, in chapter 7 we started looking at this new problem, right? We originally had, all throughout this class so far, differentiation. We're looking at slopes of tangent lines. Now in chapter 7 we've introduced this integration stuff. It's a seemingly unrelated problem of I have a curve, I want to find the area under the curve between two values of x, between a and b. So we defined that area. We said, well, that area, we'll denote this by this symbol that we call the definite integral of f of x dx from a to b. And last class we went through this very complicated process of defining exactly what this area should be, slicing this into rectangles, or really slicing into strips, and then approximating the area of each strip of the rectangle, and observing that if you let your rectangles become thinner and thinner and thinner, so you have more and more and more of them, you'll get the exact area at the end of the day if you take the limit as you let your number of rectangles go off to infinity. So we formally define this expression, this definite integral, to be the limit as n goes to infinity of this complicated summation. And we're never going to use that summation because it's too hard to use. It's possible to do it for a few simple cases, but there's no point. It's extremely hard to use. So over here we had a complicated limit definition. Hard to use, we had an easier way to do it at the end of the day. This is what the fundamental theorem of calculus is going to do for us. We've got this very, very complicated limit expression for integrals. The fundamental theorem of calculus is going to make a lot of these much easier, and we won't have to worry about the limits behind the scenes at all. So, without further ado, here is the fundamental theorem of calculus. Forevermore, if I ever write this name again, I will just call it the FTC, fundamental theorem of calculus. And it says the following. It says if you want to compute this integral of f of x dx, all you have to do is the following. You have to find an antiderivative, hence why we did this antiderivative stuff to start with. You have to find an antiderivative for f, for little f, so big F, and evaluate it at the upper bound b, and evaluate it at the lower bound a, and take their difference. So, where big F of x is any antiderivative for little f of x. And since you're allowed to take any antiderivative, you might as well take the simplest one, where c is 0. Alright, so i.e. take c equals 0. And with this, we've come full circle. Right, we started off studying antiderivatives without sort of knowing why, just that they're related to differentiation somehow. And then in the last class we started studying this idea of areas under curves. Well, it turns out they're intimately related. If you want to find the area under the curve, what you can do is just find an antiderivative for this function, and then evaluate the endpoints. Really surprising result. Really surprising that essentially what this says is somehow areas under curves and slopes, this differentiation process, actually have something to do with each other. They don't seem like they should. And it is a surprising result. Not only that, it says that the area of the curve only depends, at the end of the day, on the value of this function, the antiderivative, at the two endpoints. Everything in between sort of gets washed out. So very surprising. And again, it relates back to everything we've done so far. It says that if you want to find areas, you find antiderivatives. And what does that actually say? That says the following. This says that integration is really, essentially, and in some very strong sense, is really just antidifferentiation. Right, so integration and differentiation are inverse processes. Right, they undo each other, is really what this is saying. It's sort of parsing this all for you. So what I mean by that is the same way as addition and subtraction are inverses, multiplication and division are inverses, exponentiation and logarithms are inverses. Integration and differentiation, this is how you should think of these forevermore, this is how they're related, they're inverses of each other. Integration is just anti-differentiation, and differentiation is undoing the integration process. So really surprising result. I'll say one more thing. I didn't quite leave myself enough space here. But notationally, when you're working through these problems, quite often people denote this f of b minus f of a as just capital F of x. They'll put a bar after it, and from a to b. And what this means notationally is just plug in b to get f of b, and then subtract off what you get when you plug in f of a. And I will use this notation for all the examples I do. You'll see sort of why it's nice as we go through these problems. So for example, let's find the integral from 1 to 3 of 1 over x dx. Okay, fundamental theorem of calculus says all I have to do is find an antiderivative for 1 over x. That's it. So as long as you remember your antiderivatives, this one's not hard. Antiderivative of 1 over x is ln of the absolute value of x. And then I'm going to evaluate this at the endpoints. So I'm going to plug in 1, well I'm going to plug in 3 first, and then 1. This is why this is nice notation, because you can break this up compartmentally into two different steps. 1, find the antiderivative, and 2, plug in the endpoints. So this will be ln, I won't even keep the absolute value signs because this is positive 3 and positive 1. ln of 3 minus ln of 1. ln of 1 is of course 0, so this is just ln of 3. Or if you want a decimal approximation, that's about 1.09861. And that's it. That's the exact area under the curve. If you graph 1 over x, and you wanted to know the exact area from 1 to 3, and there's reasons to want to do this, the exact area, this area, is exactly equal to ln of 3. By the way, at the very end of last class, this was an example we did where we used a midpoint Riemann sum to approximate the area. But now, using this fundamental theorem of calculus, you can find this area exactly in all of what? 3 lines of work. Awesome. Okay, next one. Find the integral from 0 to 2 of 2x cubed minus 3x plus 4 dx. Well, we have the fundamental theorem of calculus to use now. So we know we just want to find an antiderivative for this polynomial. And antiderivatives of polynomials, hopefully you remember, are not particularly bad. This would just be 2 times the antiderivative of x cubed. So increase the power by 1, x to the 4th, divided by the new power. Minus 3 times the antiderivative of x, increase the power by 1, x squared over 2. And plus 4 times antiderivative of constant is 4 times x. And I'm going to put this in brackets so it's entirely clear. And that's being evaluated from 0 to 2. Don't want to clean this up at all. 2 over 4, since I don't have a whole lot of board space, I'm just going to clean that up a little bit. 2 over 4 is 1/2. And the 3 over 2, I'm going to write the over 2 there. Looks a little prettier. But still the same function, just simplified a little bit. And now we have to plug in 2 and 0. So what do we have? We've got 1 over 2 times 2 to the 4th minus 3 over 2 times 2 squared plus 4 times 2 minus, plug in 0 into our expression, and what about, I could write down the whole thing, but it's pretty obvious what happens. Plug in 0 out of 0, minus 0 plus 0 is just minus 0. So what is this? 2 over 2 to the 4th, cancel one of these 2's with one of these, we've got 2 cubed, so that's just 8. Cancel one of those 2's with one of those, and we've got 3 times 2, which is 6, minus 6, plus 8 again. 16 minus 6 is 10. So hopefully you appreciate how powerful this is. And how it relates everything we've done so far in Chapter 7 back to each other. Right? We've got this question of finding areas under curves. Well, finding areas under curves, evaluating these integrals, amounts to finding antiderivatives, which we've already talked about. And finding antiderivatives relates back to differentiation. So again, I think this is a good point now to sort of try one on your own. If you want to stop the video here, try this problem. Find the integral from 2 to 3 of 2 over x cubed minus 3 over x to the 4th. And it'll proceed exactly the same as the other problems. Find an antiderivative, taking the easiest one where c is 0, and then plug in the endpoints, 3 and 2. Take the difference. So just going through this quickly, I don't know how to find antiderivatives of 1 over x cubed or 2 over x cubed, but I can work with powers of x. So I'm going to transform this into something I know how to work with, which is 2x to the minus 3 minus 3x to the minus 4. And now we can find antiderivatives of these just using our standard sort of power rule, right? Increase the power by 1, divide by the new power. I'm going to drop the integral sign here because I'm actually integrating at this point. So what do we have? We've got 2x to the, increasing the power by 1, always a little bit confusing because it's negative. 1 bigger than minus 3 is minus 2. Minus 2 divided by minus 2. Minus 3x to the minus 3 divided by minus 3. From 2 to 3. Let's see. I'm going to clean this up a little bit. 2 over minus 2 is just minus 1. So that'll be minus 1 over x squared. I'm going to go back to over x squared because it's a little bit easier for me to think about that when I'm plugging in numbers. And minus 3 over minus 3 becomes plus 1 over x cubed. And that's evaluated from 2 to 3. And we'll just plug in our numbers now. We're looking at minus 1 over 9 plus 1 over 27, whatever that is, minus, plug in 2, minus 1 over 4 plus 1 over 8. And now you do some fancy algebra to put these over a common denominator. Doesn't look like they're going to have anything in common for quite a while. You'd have to do 27 times 8, I believe. It's a really big common denominator. But what I will do is at least group like things together, or expand out as minus. So let's put the positive stuff first. We got 1 over 27 plus 1 over 4 minus 1 over 8 and minus 1 over 9. And I won't write that as a single fraction, but there is the answer. Alright, so we're just cruising through these. We're just going to do a couple more examples. And that's the best way to learn this stuff, is just example by example, I think. But here's another one. It's the integral from 0 to 4 of 2x times the square root of 16 minus x squared. And by the way, hopefully this whole section is feeling pretty nice to you now, because as long as you were good at antiderivatives to start with, if you need to go back and brush up on it, you'll sort of appreciate the fact that really all we're doing here is finding antiderivatives. It's with one extra step, plugging in these bounds, but that's all the work. So if you're comfortable with chapter section 7.1 and then 7.2 on substitution, this should feel pretty good to you. And you'll notice here that my integrand is much more complicated than our first few examples. All right, this isn't a simple polynomial anymore. I've got 2x times the square root, and inside the square root I've got a function of x, so I've got this composition going on. And I'm immediately thinking, well, I can't integrate square root of anything except just square root of x or square root of u, so I probably need to make a substitution. I probably want to turn that into u. So we'll try that and see where it gets us. We'll let u equal 16 minus x squared, and that means du, our derivative, du dx is going to be minus 2x. So du is minus 2x dx. Well, what do I have left over? I've just got 2x dx there, right? So let's solve for 2x dx. 2x dx would be minus du, or minus 1 times du, all right? So let's see, where do I want to write this? So this becomes the integral of 2x dx is minus du, so I'll write the minus out front, minus square root of u du. And now we've been successful with our substitution. As long as there's no x's left over, as long as everything's in terms of u and du, then we've successfully substituted. Hopefully it looks simpler than what we started with. I think you'd agree absolutely. Square root of u is much simpler than this expression here, and something I actually can integrate. The only thing left to do is worry about these bounds. 0 to 4. But those are bounds on x. This is the problem. This is why I'm going through this example in particular, where we do a u substitution, is because these bounds have to change. These are bounds on x. It tells me x goes from 0 to 4. What does that mean u ranges between? What is u, what are my bounds on u? And it turns out it's pretty easy to compute these things. You just have to plug these into your function or your substitution that you made. Alright, so here, if x is 0, then what's u going to equal? If x is 0, u is 16. And it turns out, for reasons, that's my new lower bound. So plug in your lower bound, 0, into this function, into your function, u is whatever function of x, and whatever number you get as your output, that's your new lower bound on u, so 16. And similarly, upper bounds, if x is 4, u is what? If x is 4, u is 16 minus 16 is 0. So my upper bound is 0. You might not like that. You might say, hold on, am I allowed to have a bigger lower bound than my upper bound? Yeah, it's not a problem. It's a little bit aesthetically unpleasing, but it's not a problem. Okay, haven't managed my board work very well here. Everything's, I don't have a whole lot of space, but I think we can finish this now. So this becomes integral from 16 to 0 of minus, I'm just going to write this as an exponent because it's easier, minus u to the 1/2 to u. And we'll integrate that. So integral of minus u to the 1/2 is minus u, I'm going to leave a little bit of space, minus u to the 3/2 divided by the new power. Dividing by 3/2, but dividing by 3/2 is the same as multiplying by the reciprocal, multiplying by 2/3. So minus 2/3 u to the 3/2. And this goes from 16, from 0 to 16. Or 16 to 0. Okay, and the other thing I'll point out here is since these are bounds on u, these are actual bounds on u, I can plug them in now. And this is something a little bit different than what we did with the substitution on indefinite integrals, is we'd make our substitution, we'd find our antiderivative in terms of u, and then we'd back substitute, we'd go back to x. Here, because I've changed my bounds to u on definite integrals, the bounds make a difference here, because I've changed my bounds to u, I don't have to back substitute. I'm never going to go back to x here, I'm just going to plug in these numbers. So this is minus 2/3 times, I'm going to factor out the minus 2/3 here, so I'm thinking of it like this. Minus 2/3 u to the 3/2. So plug in 0, we've got 0 to the 3/2, minus 16 to the 3/2. And I am completely out of space. I really apologize for the board work on this problem. This is minus 2/3 times 0, minus 16 to the 3/2. Use a calculator if you want, but you shouldn't need to. Take the 1/2 power first. That's square root of 16, which is 4. And then 4 cubed. 4 squared of 16 times 4 is 64. 64. Meaning our final answer is minus 128 over 3. Oh, always ask yourself, does your answer look reasonable? Well, I'm finding the area under this function. I'm finding the area under this function as x goes from 0 to 4. And from 0 to 4, this function is always positive. Meaning my area under the curve should be a positive number. Here I have a negative. And I immediately caught that I'd done something wrong because I knew I should have a positive number. And I'm claiming it's a negative. So always ask yourself, is your answer reasonable? And what I missed is I've got minus times minus makes it positive. 128 over 3. I think we're making good time, so let's just do one more. Do I want to do one more? There's one more thing I want to mention about the fact that this lower bound here is bigger than the upper bound, which is a little bit odd. Nothing wrong with it mathematically, but again, it's aesthetically unpleasing. So after we do one more example, I'll come back and I'll mention a property of integrals that you could have used there to make it look nicer. Alright, integral from 0 to 2 of 4x cubed times e to the x to the 4th. Again, pause the video if you want, try this one on your own. It should be very similar to the last one. I've got e to a function of x, I've got this composition going on, I can't integrate these compositions. I'm thinking I need to make a substitution. The only thing I can integrate is e to a constant times x, or e to the x. So I'd better just take this whole thing and turn it into u. So we'll let u be x to the 4th. Again, if you want to try this one on your own, pause the video here, make this substitution, and then see what you get. But if u is x to the fourth, that means du dx is 4x cubed, so du is 4x cubed dx. And this then turns into, well, hold on, there it is right there. 4x cubed dx just becomes du, and we've got e to the u. With, again, remember, one more catch is I can't use these old bounds. These are bounds on x. I need to figure out what my new bounds are going to be. So we just plug them in. If x is 0, then u is, well, if x is 0, u is going to be 0 to the fourth. So still 0, actually. So my lower bound, my new lower bound on u is 0. And if x is 2, then u is 2 to the fourth. 2 to the fourth, I think, is 16. So integral from 0 to 16. And remember that. It's a really common mistake for students to forget that you have to change your bounds when you make a substitution on these definite integrals. But from here, integral of e to the u is e to the u, evaluated from 0 to 16 using the fundamental theorem of calculus. We just have to plug in these numbers. This is e to the 16 minus e to the 0, plugging in 16 and 0. And if I simplify this just a little bit, e to the 16 is a huge number, minus e to the 0, remember that's not 0, anything to the power 0 is 1. So that's e to the 16 minus 1. And it's amazing that I can find the exact area under this curve in very little work. Just a handful of lines of work, and this is a complicated number, right? E is a complicated number by itself. It's this irrational number raised to the 16th power minus 1 is the exact area of the curve, but in 5 lines of work, I can tell you exactly what the area is. It's just astounding to me. Okay, so back to what I was discussing before the last example. Just a few properties of definite integrals that you might want to use from time to time. I'm sort of fitting them in awkwardly here. Maybe I should have done it at the end of the last section. But anyway, here they are. One is the following. The integral from a to b of f of x dx is very closely related to the integral from b to a of f of x dx. And how are they related? They're not equal as I've written here. They're negatives of each other. Alright, so this means that you can freely interchange your bounds, you can flip the upper and lower bounds, as long as you introduce a minus sign when you do it. So 2 examples ago when we had, I think, the integral from 16 to 0, if you didn't like that, if you didn't like that your lower bound was bigger than the upper bound, you can flip them if you want, just throw a minus sign out front. 2. Here's one that's usually written, although it's obvious now that we have the fundamental theorem of calculus. The integral from a to a of f of x dx. Well, you could show that you could use the fundamental theorem of calculus and say this would be okay. Capital F of x evaluated from a to a, so big F of a minus big F of a is of course 0. You could see this geometrically. What's the area in this curve from a to a? Well, this has no width, so the area is of course just 0. Geometrically that must be true. So worth remembering, if your upper bound and lower bound are the same, the integral is automatically just 0. But this one's a bit more interesting. 3. Integral from a to c. We'll go a to b. A to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx, where c is any real number. And I'm going to parse this geometrically in the most sort of obvious way. I'm allowing here c can be any real number, but I'm going to parse this using the case where C is something between A and B. So here's what we have. We want area under the curve from A to B. Right? We want this area. Well, think of C as being something in between. Think of C as being some number in between A and B. So you choose C. Okay? Well, what's this area? That area is the integral of the function from A to C. Right? That's the integral from A to C of f of x. What's this area? Well, that's the area from C to B, right? So that's the integral of the function. That's the integral from C to B of f of x. I'm leaving the dx's off of the end there because I'm being lazy. But obviously then, if you add these two areas together, add this area and this area together, you would get the whole area back. So if you take the integral from A to C plus the integral from C to B, add them together, that should be the area from A to B, the integral from A to B. So geometrically, this is sort of an obvious result in that you can introduce numbers between A and B, really any number at all, and split up your integrals and add the areas together piecewise. So just three interesting properties of integrals you might want to use from time to time. So we'll do one more example that leads into our next section, area between curves, but we can actually tackle stuff like this right now. So it's an area problem. It's find the area between the x-axis and the graph of f of x equals x squared minus 2x, and we're going to do this from minus 1 to 2. And your first instinct might be, well, okay, I want the area, so I'm just going to go integral from minus 1 to 2 of x squared minus 2x dx. But it turns out if you compute this, you'll get the wrong answer. And I'll show you why. So let's try and let's graph this function. Let's figure out what this looks like. So when does it cut through the x-axis? When is y equal to 0? So x squared minus 2x, when does that equal 0? Well, let's factor out x. X times x minus 2 equals 0. So that means x is 0 or x is positive 2. All right, two different roots here. Either x is 0 or x is 2 for this to equal 0. All right, so we're interested in going from minus 1, here's minus 1, to positive 2. I know roughly what this looks like. This is a parabola, an upward opening parabola, because it's a quadratic function. And I know that it cuts through the x-axis at 0 and 2. And it's upward opening, so it must look something like this. All right, so what are we asked to do? We're asked to find the area between the x-axis and the graph of this function. So we're looking for, well, there's the area between the graph and the x-axis. We're looking for the sum of these two areas. All right, we're looking for the sum of these two areas. And I've already told you that the area is not going to be the integral from minus 1 to 2 of our function. And now that we have a picture in front of us, why is this the case? Well, remember how integrals work. The integral from minus 1 to 2, that would count all of this stuff. That would count all of this stuff as minus, negative area. Right? Definite integrals give you the net area under the curve. So that would be giving us the area of this region minus the area of this region. But when you're talking about area like this, when it asks what's the area between curves, area between curves is always a positive number. It doesn't matter whether you live above or below the x-axis, it should be a positive number. So what we really want is the area of this region plus the area of this region. and this integral is going to subtract that stuff. So we need to be more careful. So how do we handle this? I don't like the way I've handled it in my notes. So, what's the area going to equal? Well, let's call this, let's give these two regions names. How about we call this region, we say that's R1. And this region here, we'll call that region R2. So the area is going to be region 1 plus region 2. And now we just have to find these things separately. I think I have everything that I need. Minus 1 to 2, 0, 2, I haven't written down what my function was. It was x squared minus 2x. So we'll work these out separately and then add them together. So region 1, area of region 1. Well, that's just the area below this curve from minus 1 to 0. Alright, so minus 1 to 0 of x squared minus 2x dx. And this is no problem. Fundamental theorem calculus says, okay, find an antiderivative. 1/3 x cubed minus 2x squared over 2, so just minus x squared, evaluated from minus 1 to 0. And if we plug in 0, nothing particularly interesting happens. It's just 0 minus 0. Minus, be careful with this part. This is a really common mistake. Make sure this minus distributes to the whole thing. So now we plug in minus 1. We're looking at minus 1/3. 1/3 times minus 1 cubed is minus 1/3. Minus 1 squared is minus positive 1. So that is what? So we'll distribute the negative. That's 1/3 plus 1, which is 4/3. Okay, so R1 has area 4/3. Now we have to deal with R2. So, what's the area of R2? Well, if I just said, okay, I want the integral from 0 to 2, we'll take the integral from 0 to 2 of x squared minus 2x dx. That would give us negative of this area, right? Because it's below the x-axis, this counts as negative area. I promise if you compute this integral, you'll get a negative number. So how do I fix that? Well, if I want this to be positive again, I can just multiply by minus 1. And that's all I have to do. Just whatever number I get, multiply the whole thing by minus 1, because I know it's going to be negative at the end of the day. So multiply by minus to make it positive. And that should suffice. Another way you can handle this is think of taking the absolute value of that expression if you want. I could work the minus in here. I could interchange the bounds, make this 2 to 0, and the minus would go away, but we don't need to. This would just be minus, let's see, 1/3 x cubed. We actually already did this last time. We found an antiderivative. 1/3 x cubed minus x squared, going from 0 to 2. So this will be minus, and now we'll plug in these numbers. 2 will be 8/3 minus 2 squared is 4. Minus, what do you get when you plug in 0? Just 0. Lots of brackets here to make sure all the minuses distribute properly. But anyway, what do we have? We've got minus 8/3 minus 4. How many thirds is 4? That's 12/3, right? So 8/3 minus 12/3 is minus 4/3. As promised, this integral is going to give us a negative number, but multiplied by minus 1 now makes it positive. That's 4/3. surprising. These two shapes don't look the same at all, but they actually have equal area. The area of R2 is also 4/3. And I'm just going to box this off separately instead of erasing everything. What does that mean our total area is? The area between the curve and the x-axis is 4/3 plus 4/3, which is 8/3. So be careful. Be careful when you're thinking about if the question is to find a geometric area, an actual area between two curves, be careful to think about whether your integral is going to include minus negative stuff. Because you don't want to subtract that area away, you actually want to add it. And to handle that, you might have to break your integrals into different pieces. We'll do more of this in the next section. We'll do lots of area between curves in the final section, 7.5. And we'll do one more business or economics application to illustrate reasons why a person might want to, say, find areas between curves. Thanks.